Aside from the place where you're likely to find absorptions for specific groups, which we would have discussed in a previous video, aside from these specific chemical shifts associated with specific structures in a molecule, there are relative changes that come from having an electronegative atom nearby, one of those features. So remember that electronegative elements pull electron density away from hydrogens. That leaves the hydrogens just with the presence of the external magnetic field, and if there are few electrons around them, then those electrons won't be able to oppose the field very much, and the net field will be relatively strong. So when you have electronegative elements nearby, it ends up reducing the push back against the external magnetic field, and it increases the strength of the magnetic field that each nucleus feels. Because the strength of each magnetic field is larger, it's harder to flip the nuclei. In other words, you need more energy to flip the nuclei. And so the shifts will get larger, the chemical shifts will get larger, because they represent how much energy it takes to flip a nucleus in the net magnetic field. So having these electronegative atoms nearby will increase the amount of energy that it takes to flip different types of hydrogens. Now if you have an alcohol or an ether, so that's just an OH or an oxygen with carbons on both sides, remember that capital R means any carbon chain. If you have an alcohol or an ether, that will shift the expected peak up, or in other words to the left, by 2.5 parts per million. So, for example, if you would expect this methylene group to appear at around 0.9, if an alcohol or an ether were right next to the hydrogens, then you would have to add 2.5 to that. If instead of an alcohol or an ether, it's an ester, and an ester is when you have a carbon double bonded to an oxygen, single bonded to an ether. So notice this is different from an ether. Always watch out for this carbon double bonded to an oxygen, which is called a carbonyl. If you have the carbon on the ether side, so that the carbon that's exposed to both of the oxygens, that is increased by the effect of the electronegativity of both oxygens. It loses a lot of its electrons. It can barely fight against the electrons barely push back against the external magnetic field, leaves a very strong net field. It's very hard to flip nuclei, hydrogens that are near an ester. And so you would add 3 energy units, 3 parts per million to the shift. So if normally these CH2s would cast a shadow at around 1.2 parts per million, in the presence of this ester, you add 3 more to that and they would actually cast a shadow at 4.2 parts per million. It's harder to get them to flip when all their electron density is being stolen by this group. Last but not least, if you have a carbonyl, and a carbonyl is a carbon double bonded to an oxygen, if you have that, then you would just add 1 to the parts per million. Now watch out, if you have a hydrogen, if you have an ester, and the hydrogen is on the carbonyl side, so not the side with the oxygens, but the other side, then you'll treat it as a carbonyl group rather than as an ester. Okay, this is if the hydrogens are right next door. They're on a carbon right next door to the thing you're interested in. And that's called the alpha position. So let's say you have an alcohol, that's what you're interested in, the carbon right next to that, that's the alpha position. And then as you go down a carbon chain, you can refer to those carbons away from your reference point with letters in the Greek alphabet. So the first one is alpha, the second one would be beta. If you kept going, it'd be gamma, delta, etc. Just going through the Greek alphabet. Now these numbers here are for alpha protons. They're for protons, hydrogens, that are on the alpha carbon. If the protons are on the beta carbon, they still feel the effect of the electronegativity. It's just around a fifth of what you would expect for the alpha. So for the beta, if you have hydrogens beta to an alcohol or an ether, it's a fifth of 2.5, that's 0.5. That's what you'd add. If you had hydrogens that were beta to the oxygen side of an ester, you would add a fifth of 3, that's 0.6. And if you had hydrogens that were beta to a carbonyl, then you'd add a fifth of 1. That would be 0.2. So the numbers they're giving you in this table are for the alpha carbons, for hydrogens on an alpha carbon, and for a beta carbon it would just be 1/5 of those. Okay, so we'll do a bunch of practice with this in other videos, but I just wanted a quick video to introduce this idea. You have the places where these peaks are likely to occur just because of the structure of these groups. So you have the chemical shifts where they're likely to occur, but those chemical shifts will change if you have very electronegative groups nearby. And the amount they'll change depends on what the group is and how close they are. So they have the alpha shifts if the hydrogens are right next door to the group, and the beta shifts if they're beta to the group, 2 carbons away. So we'll apply these two tables, we'll use these two tables in the next video.